Thank you very much, Regina, for the nice introduction. And we have heard something from Harish about sustainability in the inhalers themselves. And now let's have a look on the raw materials, on the polymers, how to design materials for inhalation devices to be more sustainable. Sustainability, what are the consequences for plastics? We see and we face negative image of plastics and trend to use alternative materials. We also face need of reduction of the carbon footprint of the materials. We see stricter regulations coming and restrictions for plastic usage. And when we look into the statistics, we see that the global plastic waste is roughly 300 million tons. And for single-use biopharma, we talk about 30,000 tons. This goes along with the healthcare polymer consumption globally to be less than 5% and the waste stream to be less than 0.01%. What does this mean? Healthcare plastic waste is less significant, but we cannot and we should not ignore it. So what can we do? What are the first steps and feasibility in healthcare? We can reduce our carbon footprint. How? Using alternatives, biosourced feedstock polymers. We can reduce our material itself. And how do we do that? By using chemical foaming agents, which are already routinely used in automotive and also in food packaging. So why not in healthcare? And then last but not least for today, we will look into alternative formulations, material design solutions. Then there are some other possibilities, which I will not go into detail today. Reduction in carbon footprint. We want to replace the fossil-based polymer with a bio-based polymer. The status quo is that more than 60% of plastic pharmaceutical bottles use polyethylene, and more than 30% of devices are based on polyethylene or polypropylene. The challenge is to maintain similar properties and similar regulatory status, and we have to look into the total system, not only the polymer, but also into coloration and into functional additives. The solution is that there are polyolefin feedstock available, which is up to 95% bio-based. However, there's no medical or pharma grade yet available. But the positive news is that there are already concentrate or master batches or ready-to-use compounds developed on bio-based polyolefin feedstock, which means that we can also have the polymer as well as the colorant would be tested to ISO 10993 or USP 8788, just to name a few. Polyolefins from bio-based, we expect similar properties, but we want to have a better carbon footprint. So let's have a look on the coordinative system of biopolymers. Here you can see on the left-hand side the life cycle analysis of polyethylene. On the lower corner, we have the life cycle analysis of fossil polyethylene, and for 1 kilogram production, we would also produce 2 kilograms of CO2 equivalent. When we look into sugarcane in bio-based polyethylene, by producing 1 kilogram of this polyethylene, we have 260 grams of CO2 equivalent consumed. So definitely a much better footprint, carbon footprint. This was about the polymer, but what about the colors and functional additives? The possibilities are here that we can have inhalers and disposable pharmaceutical containers with a bio-based content up to 90%. This would be a drop-in solution with a reduced carbon footprint. There would be no change in processes needed and potentially minimal impact on regulatory status. So there is a full portfolio of colors and additives already available using a bio-based rather than a conventional polyethylene or polypropylene. And they come with the benefits of same regulatory documentation based on pre-tested ingredients according to healthcare standards like USP, ISO, EP, ICHQ3D, and more. Good news is not only the colors and additives has been tested, but also the biopolymer, meaning the carrier, has been tested, and they come with a change control produced in plants which are ISO 13485 certified. Secondly, we said we want to reduce the material usage. We can do that by reduction of the weight with chemical foaming agents. Chemical foaming agent can be used in injection molding, in extrusion, and also in blow molding. On the left-hand side, you now see the results of a trial with a polypropylene homopolymer. When we adapt the injection molding parameters, we can reduce the weight of the sample from 14.4 grams down to 11.4 grams, meaning a reduction of 14%. But we can also have up to 20% material saving with these chemical foaming agents, up to 50% shorter cycle time, up to 20% reduction in climbing force, and on top, there's no need of additional machine investment. Secondly, we can reduce the material usage with material design solutions. We want to replace and reduce the fossil fuel-based content to come to an amount of below 50%. How do we do that? Combining raw materials, non-fossil fuel-based resins, with natural and synthetic mineral fillers and non-fossil fuel-based colorants and additives. Let's look at an example, ABS. ABS is a material of choice for medical devices with a nice balance of properties. But also it has some negative aspects. It's based on fossil raw materials, obviously. So here the possibility would be that we design a material solution with a bio-based polyolefin baseline instead of using a conventional styrenic-based baseline. And then we modify this material with other non-fossil fuel-based ingredients to reach the truly needed balance of material properties. And at the same time, we would have a solution with over 50% of bio-based raw materials. So let's discuss your requirements and our ideas. So a short nutshell summary here. The first steps to increase sustainability in healthcare are designing devices using bio-based polyolefins and bio-based color and additive master batches. We also have seen that by using chemical foaming agents, we can reduce the weight and we reduce the plastic consumption. And last but not least, by designing alternative formulations in form of compounds, the fossil fuel-based content and even the plastic content itself can be reduced. For further insights, please contact us, and I would like now to open the floor for questions. Thank you.
Thank you, Beate, for that presentation. I have a question related to those, for example, sugarcane PE. It sounds very promising, and the let's say obvious question is, why can't we change or replace all the fuel-based PE directly with sugarcane PE? Is it because of lower availability, maybe of missing industrial capabilities, or why can't we just replace it one by one?
I would say this is a mix of both. First of all, it's a question of availability and resources. Yeah, that's the main, and then the infrastructure around it, and then on top of that you have the cost. Yeah? If you look at the oil price at the moment, we see a really low price, and this of course has a tremendous influence on the polymers and the prices of the polymers. And then it's not so easy to switch from one to the other if there's not also, let's say, from a commercial point of view, at least some driver or not a big obstacle. Yeah.
Okay, thank you very much.